Is my screen is visible?
Yes, sir.
Okay. Atharva, why you are online? Yesterday I saw you were there in the class. Now you are on for lectures. You are online. Okay, think. So we were talking about electromagnetic waves, and we saw that it's not just simple wave. It's not just simply a simple wave. It has some more properties, which was del dot E is equal to 0, del dot B is equal to 0, and del cross E is equal to minus dabba B by dabba T, and del cross B is equal to mu 0 epsilon 0 dabba E by dabba T. So these properties gave us more things, right? What were the things? First one, the divergence told us that it is a plane wave. Okay, so there is no component. Suppose we consider the plane wave, there is no component which is perpendicular to the, sorry, there is no component which is parallel to the direction of the propagation, but rather all components are perpendicular to the direction of the propagation. So EM wave transverse, right? It's a transverse wave. What second thing we got? This is for from the divergence of E and V both. From the curl, we got another information that I'm writing one of the information. Omega, then Z cap cross E0 to E, right? This we got from the curl. Okay. Now this particular expression is giving us what kind of information? The first information, suppose you take a mod. Okay, you get one more thing, e raised to not mod. So from here you directly get one part. Delta B is equal to e raised to I delta E. You have exponential component on both the sides and a real part. Okay, you can just take out the real part separate and exponential part separate, right? Exponential part has to be equal to each other. Then and then real part will be equal to each other, right? And exponent part which will be equal to each other. So exponential part e raised to I delta B on the left hand side and e raised to I delta E is on the right hand side. That implies that delta B is equal to delta E. So both E and B fields are in phase with each other. Okay, the phase difference between E and B field are basically 0. Because what is this delta B and delta E? It's a phase of B field and E field. Right? Similarly, we go out one more thing. Now suppose we take a real amplitudes B0 and I just take a magnitude, it is K by omega of E0. Now what is K by omega? K is equal to 2 pi by lambda and omega is equal to 2 pi f or 2 pi by t. So what will be K by omega? One upon V. So that is equal to 1 upon V E0. That is okay. Okay. So you can see that even in electromagnetic waves, B0 is like scaled down by 1 by V, the speed of electromagnetic wave in that particular medium. Okay. We write this one as 1 upon the V is written as 1 by C for the reason that speed of electromagnetic wave in free space or vacuum is considered as C vacuum, right? Which is 3 into 10 raised to 8 meter per second. Now we can look at the different properties of the electromagnetic field. First one, there is the energy stored in the electromagnetic field. So we know that energy density in electromagnetic wave is basically half of epsilon 0, because it is both the fields, E square mu 0. One part is because of the first part is because of the electric field, second part is because of the magnetic field. But we know that E and B are not separate. Their amplitudes are not separate from each other. So we can connect them with each other. How we can connect? If amplitude is has some relationship, that means wave has that same relationship. So B will be B square by mu 0 will be replaced by what? 1 by mu 0, 1 by C square, right? And this will be E square, right? But C is equal to what? 1 upon square root of mu 0 epsilon 0. So that implies that this expression is given by 1 by 2 epsilon 0 E square plus what will be here? Mu 0 will cancel out. What remains is epsilon 0. 1 by C square is nothing but mu 0 epsilon 0. Mu 0 will cancel out, and it also becomes epsilon 0 E square, and that gives us, right? Right now, when I'm writing in terms of energy, I'm writing in real amplitudes, real wave, not the complex one. What will be S? What is the formula for S?
1 upon mu E into E cross.
What is the
B.
formula for S? Wait. I can't hear you because of the mask. I can't see your lip movement. So what? This is called vibrations. You don't know the formula. One by mu naught. Now for a EM wave, we already know E and B are perpendicular to each other. Okay. So E cross B should give us a Z cap, which is the direction of the propagation. Okay. So 1 by mu 0. And E and B are connected to each other. Right. That is, you write E and B is written as E by C. Okay. Z cap. So that is written as 1 by mu 0. This is E square by C. Sorry, Z cap. That is okay. Now we got mu 0 also, and C. We know that C is 1 upon mu 0 epsilon 0, right? So even we can do that also. We can write mu 0 epsilon 0 divided by, sorry, what we can do is that we want to see, we know mu 0 is there in C. So we can just try to add that by some way. Can anyone tell me what we can do? We can convert mu 0 to C, because C is easy to see, because C is the speed of light. So which is measurable quantity. So what we can do is that if you take mu 0 epsilon 0 and also mu 0 here, we get square by C Z cap, and mu 0 epsilon 0 is 1 upon mu 0 epsilon 0 is C square. Okay, so this gives us what? C epsilon 0 E square Z cap. That is okay. And we know what is this? This is nothing but U. So C into U Z. So what it says, what this statement is saying, S bar is a flux. And right hand side exactly shows that speed with which the energy is flowing. U is the energy stored in the energy density. So if energy density is flowing with this speed C, it is carried by that much mass. Then we also have a electromagnetic momentum, right? What is the electromagnetic momentum? Density. I'll talk about the density. Small p. Clinton. Small p. Electromagnetic momentum density. Last bench. So mu 0 epsilon 0 S, right? Or S bar by C square. This is your momentum density. We have seen now S has a dual purpose quantity. Simply S shows the flux, mu 0 epsilon 0 S bar shows the momentum density. S is like a dual purpose quantity. So you can write down, find out what is this. Because S we already know mu 0 epsilon 0 is C square. So it is U by C. Right? Okay. Then we can talk about one more quantity which is experimentally observable quantity called as intensity. Suppose the electromagnetic wave is hitting a surface, then or electromagnetic wave is going, what is the intensity of that particular wave? Okay. So what is the intensity? What is the meaning of intensity? So amount of energy transferred per unit area per unit time, right? Now can anyone tell me it is related to which quantity? Amount of energy transferred per unit area per unit time is connected to what kind of quantity? Any quantity which has a similar type of definition. Pointing vector has the amount of energy carried per unit area per unit time. So we can see that this is some way should be connected to S. Right? I have not written final answer, but it should be connected to S, no doubt about that. Okay, the question is how it is connected. Okay, that is the next question. The intensity is something which we measure by a particular instrument. So what instrument is going to do? It is going to measure the amount of energy hitting a surface for a particular time, and divide by that time should give us amount of energy per unit area per unit time. But now what the instrument is doing, it is adding all the energies which is hitting the surface. That means it is doing a job of integration and then dividing by delta t. So what it is doing, it is taking a kind of a average energy. So you don't see a wave, but you consider as an average energy. Actually, the energy is carried in terms of a sine wave, right? But we are taking an average. So what we should do is that S is the amount of energy per unit area per unit time transferred from the surface. Okay. So suppose you take an average of this. Then you can connect it to this, right? Just consider the surface area through which the energy is getting transferred is the surface area of the instrument where the energy is basically observed. So we can say that I is equal to average value of S. Okay, they are simply connected to each other. Now the next thing, if you want to take an average value, we know that it's a periodic function. So you don't need to calculate average for everything. just calculate average for a single period, that is good enough. So suppose you take an average over a single period, what you will get? 1 by t of integration from 0 to pi sorry, of the function, which is basically, if you take a real function, it's a cos, or take a complex function, integrate it, then take a real one. Even that is also. Are you have done the RMS value? Huh? No, but I am asking the question, what will be the average value? How the average value will look like? See, we have done this type of mathematics already. But then we have done similar type of thing. Now, what is that? You take a DC multimeter, DC voltmeter, connect to a AC signal. What that is going to do? It is going to measure a voltage and then going to take an average of that, which we call as the RMS value. So that is what it is. This is also doing, right? So what will be that? That is like dividing by 1 by 2, right? What divided by 1 by square root of 2, right? Square root of 2, 1 by square root of 2, right? So average value of S, which is basically C into epsilon 0 E square. Now if you take an average of this quantity, now understand, you are going to take an average. When you take average, C and epsilon is going to remain same. Average will be over E square, so that 1 by square root 2 will be basically half. It will be now E square, or what will be here? Last part. Will it be E square? Last bench. Now what should I write here? So I have taken average of this, right? Now I got an answer. Should I write E square here or something else? Huh? करो cos square का average. No, but term contains E square, na? Average only of sine will be 0, but average of sine square or cos square will not be 0. See, E square, na, if you have a E, then there is a problem. Then it will be 0, obviously. But E square, so if you take a cos term, cos wave, it hardly matters whether you consider this as a cos wave or sine wave, just pi separated by pi by 2. So you are changing your delta, nothing else. Okay. So if you take a cos square or sine square, integration of that, it will not be 0. Rather, it will come there to be 1 by 2. Right? So I have written 1 by 2. But what should I write for E? Should I write E as it is? E naught, because E is equal to E naught into cos of kz minus omega t plus delta. Right? Now when we take square and do our averaging, the cos term is gone from the picture. What remains is E0. So similarly, you can find out average of and average of U also. This term also you can find out, which is nothing but basically a average taking average over U. Similar, you will get 1 by 2, 1 by 2 everywhere. That is okay. Is it clear this part? This is clear. Okay. So we'll go to the next part. By the way, If you look at P, what will be average of P? Ek minute, I'll just write here, that will give you idea. P is S by C square, right? So average of P should be, C is anyway constant. So 1 by C square into average of S, right? And we already got for S the direction. You can just consider direction, but 1 by C square. What will be here? It is C epsilon 0 E0 square. So half of so that becomes here you can also write I by C square. That is also okay. So your average momentum transferred per unit area per unit time is I by C square. And that is the reason we don't see a momentum getting transferred. Can anyone tell me what is the reason you really don't see a electromagnetic momentum in day-to-day life? Why? Like if you're standing in sunlight, you don't feel a force, somebody is pushing you. Why? There is no change in the momentum. At least apparently that is what we see. Why it is so? C square, right? Because C square itself is a so huge quantity, it tends to 8 meter per second. Square of that it tends to 16. You know, so you don't feel that force at all. So for you, there is no force at all. Means your body don't even sense that force. That is so small. Either you take a very, very small object, okay, or you increase your intensity very high. One of the way. So if you go very close to the sun, it means forget about the what will happen to you because of the temperature and everything. But you can now the eye might go much higher, say 10 raised to 8 times night time. That time you might feel a force, the radiation pressure, or the particle has to be so small that for the same momentum, the acceleration will be high. See, momentum will give you acceleration, right? Now your body is heavy, that's why you don't feel acceleration. That's why the earth, see, just consider this way. When we talked about P, we talked about the comet getting pushed, the particles of the comet getting pushed away from the sun because of the radiation pressure, which is because of the EM momentum, right? But why it is not happening to the earth or moon or other planets? They are heavy. The comets are made up of very, tiny, means very light particles, water molecules or any other gaseous molecules which are frozen because of the low temperature. So they are so light that they can actually show the effect of the force. The heavy objects like Earth and Moon may not show that force at all. They are feeling that force. So even the sun is getting radiation from the Earth. Earth is getting radiation from the sun. You hardly see any Earth getting pushed away in one direction. But then the intensity also plays the picture. You have to be very close to the sun to feel that force. You know how far we are from the sun? How much? But can you feel that? Feeling is important. I shared a video last year about the size of the solar system. Last year we had an experiment on plotting the solar system. So I shared a video with you because all of the textbooks or reference books which we refer related to when we are in school or in basic undergraduate schools, colleges, what we see is that there is a sun, all planets are next to that, right? So it's like it's a compact system, but in reality it is not. So Earth is far away from the sun. Okay, so that's why you don't feel I much. So when the gases which are around us, even though they are light, I is too small. So other forces play that force can be there, but other forces are so strong compared to that, you don't even feel that force at all. Like force due to the thermal motion, the change in the density of the gases because of the thermal change in the temperature, that force might be much stronger than this force. So you don't even consider that force at all. Okay, so now what we'll do? This is done. We are done with the thing. We are done with the electromagnetic wave in vacuum. What is there? Nothing. We have a wave. Okay, and we saw its properties. Right. First property is that it is perpendicular to each other. E and B, they are in phase. Then we saw what is the energy stored, momentum, and S, which is the flux, and then average value of that intensity. Then now what else we want for the electromagnetic wave? Now, as soon as the electromagnetic wave interacts with something, it is in the space. This is what happens. So story is over. As soon as it interacts with something, the things we'll see. We will see the things if it is interacting with something. Now, for that, we have to consider electric and magnetic fields in what materials, because it is interacting with something. So that electric and magnetic field will interact with the material, right? So we are done with the electromagnetic wave in vacuum, basically. Now, what we should start? Electromagnetic wave in a material, right? Now we'll take a simple case. What is the simple case? We'll consider materials are nice and well behaved, right? So they are linear materials. Okay. What are the properties of the linear materials? D is connected to E and H is connected to B by some relationship. What is that? Do you remember this relationship? We calculated this relationship. And where epsilon, what is the epsilon? Yeah, epsilon naught 1 plus so- sorry, sorry, my mistake, my mistake. Right? And your H, right? Which is again mu is also written in the same way. Mu is equal to mu 0 1 plus chi m, right? Now difference between these two quantities is that chi e is normally a good amount of quantity. So epsilon and epsilon 0 are something which are not 1 plus chi e will be some value. But in this case, majority of time chi m is of the order of 10 raised to minus 8 for majority of the materials. Paramagnetic, diamagnetic, both. Understand, all materials by default they are diamagnetic. All materials by default they are diamagnetic. The question is that some materials have their electronic cloud configuration last such a way that paramagnetic effect also come into the picture. And once it is dominant, the material behaves like a paramagnetic. But by default, all materials are diamagnetic. And all materials, what about electric field? All materials of para-electric or dielectric? The word is hardly used. Okay, find out this one. Para-electric, dielectric, what is that? The word is hardly used because it is one type of metal. We don't differentiate dielectric, para-electric, that type of thing because of only one type of material. Here we use separately in magnetic field because there are two distinct type of materials we can see. Even though underlying is dielectric only, all material, diamagnetic, sorry. And one particular type of materials have a paramagnetic effect also into the picture. So that dominates, so it becomes a paramagnetic material. So in this particular case, mu is approximately equal to mu 0 because 1 plus chi m is almost 1. 1 plus 10 raised to minus 8, 10 raised to minus 6, that range. So many of the calculations will use this range. So many of the calculations will have mu is approximately equal to mu 0. Okay. But not necessarily everywhere we will use this one. In some cases, we might go for mu is separate from mu 0. But majority of the discussion which we are going to have, mu will be approximate to mu. Now, what will be the equations for EM waves in linear materials? This is one equation and second equation. So we'll have Maxwell's equations. What are the Maxwell's equations? Say we don't have a free charge and free current, then we'll have del dot D equal to 0, del dot B is equal to 0. Then this remains as it is because it does not have any sources. So minus of. So this third equation remains as it is, irrespective of whether you are talking about the material or not. The last equation and the first equation, they are the one they which are going to change. Sorry, gamma d by, right? This is clear, and they gives us. Suppose we write this one, D and H. They will give us. If you substitute D, you will get del dot E equal to 0. This is anyway going to remain as it is. The third one again remained as it is. What about the fourth one? Del cross H. It is B by mu. Mu will go on the right hand side. D will also give out epsilon, and it will become E. So what we will get? Del cross B is equal to mu epsilon da by E by da by T. That is okay. Even if you don't write, it's okay. You don't have to write. First, understand. This is clear. Now, this equation, if you see, they are just like our equations of Maxwell's equation in vacuum, except the mu 0 epsilon 0 is replaced by mu epsilon. Right? So, the rest of the mathematics remain the same for all of them. Wherever there is a mu, will replace by, sorry, mu 0 will replace by mu. Wherever there is a epsilon 0, will replace by epsilon. Other things remains as it is. So we'll have equations like this. K by omega right, and your B is equal to 1 by C of E, right? That is okay, or you can even if read tilde, that is also. So they are the same way, they are in phase with each other, they are perpendicular, transverse wave, everything is same. So EM fields in the material also the waves in the same way. So they are also electromagnetic wave, right? Only there, sorry, I just made a mistake. Only their speed will be different, which is given by mu 0 epsilon 0. So let me call this as D. That is okay. Now we like to express V also in terms of C. We know the reason because C is a universal constant, right? It remains same in all frame of references. So we can V is equal to C by N where N can be calculated. C is 1 upon mu 0 square root of mu 0 epsilon 0. V is 1 upon square root of mu epsilon. From there you can find out N. Okay. This is done. What about S? S was V U Z cap. Right? V was it was CU na? In the vacuum. Now it is VVU. Right? Average value of S will be what? 1 by 2 of V into epsilon E0 square. Right? We had 1 upon 2 C into epsilon 0 E square. Now we had a, which is nothing but I. Similarly, you will have momentum also. That is clear? Okay. Okay. So now we got electromagnetic waves in material also. Now what? We are done with the electromagnetic wave in material also. Non-linear anyway we are not having here, at least in this place. We are done now. Technically we are done with everything. So what else is remaining? No, we got two type of waves. One in vacuum, one in material. Okay. So if you got two type of waves, there will be a starting point and end point for a material. Material will start somewhere, it will end somewhere. From there, another material might start, or it can vacuum can start. Anything can happen. So it will be always like one material will end. So let's consider vacuum also one material. Okay. One material will end, another material is going to start. Now the next question, we know the wave, electromagnetic wave inside a material. Now next interesting question will be what happens when the wave transfers from, when encounters a boundary. Not transfers, let's there is a boundary. What happens to this electromagnetic wave? What happens? That can be an interesting question. Now there are two things. There is one more thing. This is a dielectric material we have considered. Suppose we got a conductor. In that case, what will happen? We consider dielectric materials here, right? So now here we can ask the question. Suppose I got a dielectric material, okay, with mu and epsilon as my permeability, right? Permittivity and permeability. Then what happens when we reach the end? Now we know exactly what happens in the bulk part. Fine. What happens as soon as we reach the end? That is the next question. Okay. So let's consider that there is a material 1 and there is a boundary. Done? Okay. So there is a boundary, there is a material. Just give me 1 minute. Okay, there is a material, both sides. This is material 1 and this is material 2. Not necessarily there has to be a material, it can be vacuum also. Let's consider vacuum as a one material. Now what happens for a wave which is in material 1 encounters a boundary? Okay, we expect logically that some part, there are two possibilities. Either it gets reflected back or it is transmitted. So we will consider both the possibilities and work with that. Okay, that is clear. So we'll stop here. Now there will be two parts, there will be two parts. One where electromagnetic wave is traveling where the direction is perpendicular to the surface. Another case where the direction is not perpendicular to the surface. It is at some angle. It cannot be parallel. If it is a parallel, then there is no bound. Right? Okay, so we'll stop here. So we'll see both the cases one by one. Where perpendicular case is simpler one. Parallel inclined one is a slightly complex one. So that also will happen. Okay, we'll stop here.